We have Matthias here, so we can start. So welcome everyone, good afternoon. It's a great pleasure to welcome Utwin.
Otto.
If you're friend, you can call Otto. After I practice all morning.
Breitenstein.
So Otto will be here, he's a guest of Thorsten and me. We'll be here for 2.5 weeks, and we asked him to give 3 presentations. So today, next week, and week after that, and he will cover quite a lot of his work. So first of all, welcome to UNSW. We made you a bit of gifts, and as you can see...
Thank you very much.
So Otto already joined us for some outdoor measurement, and we saw that the winter in Sydney is not really winter, and enjoy the sun, so we bought you sunnies and hat. I assume that everyone know a bit of Otto work. He did quite a lot of work. He's like considered the father of clock in tomography, but his beginning was in DLTS, so his PhD was I think 1980, and it was on DLTS, and then he worked quite a lot, 12 years on scanning DLTS. He joined the Max Planck Institute in 92, I think, and from there he worked mainly on localized characterization of solar cells. Like I said, it was lock-in tomography, but he did quite a lot of other work also on PL imaging and other techniques. So what we asked Otto is if he can split to 3 topics, and I think that the first topic today is about voltage characterization of solar cells, so inhomogeneity, and next week will be on PL, I think, and the last one will be on
lock-in tomography.
So please welcome Otto. Thank you very much for coming.
Thank you for your kind introduction. So, and thank you for inviting me. And I'm very happy to be here after more than 12 or 13 years. So a long time ago, I already have been here doing some work, which also will be reflected, and I will show some results which I have obtained here. So this talk will be on physics. Maybe I should tell something about my background. So actually we are not a solar institute. So I never in my life have made a solar cell. I only have characterized them. So all my life I've spent on characterization, and I was in the fortunate situation that I could concentrate on this for all the time. So in our Max Planck Institute, I could choose whatever I wanted to research, and I decided to stay with this, and therefore I could dig quite deeply into that. So the title of this talk is The Role of Inhomogeneities for Understanding Current Voltage Characteristics of Solar Cells. And in this talk, so after some motivation and introduction, I will introduce briefly only the used characterization techniques. So the next talks will be in some more detail about luminescence and lock-in tomography. Here I will touch this only briefly, and the main part is to describe the origin and also the quantitative influence of inhomogeneities of these parameters J01, J02, and the parallel resistance, which I will explain later on. So, and moreover, I will summarize what we have found on the origin of pre-breakdown sites, which is also interesting, and one new mechanism will be introduced, and I come to some conclusions here at the bottom. You already see some of the images you will see later on. So let me start with a motivation. So please let me remind you that all solar cells are more or less inhomogeneous devices. So these simple equivalent models with a one-diode or two-diode model, actually implicitly they assume that the solar cell has the same properties in all regions, which is in reality not the case, and this holds in particular for multicrystalline solar cells. I have also to remind you that multicrystalline solar cells still represent the workhorse of photovoltaics. So about 70% of all produced solar cells until now are made from multicrystalline materials, with monocrystalline only slowly catching up. There have been predictions some years before that in some years we will have no multicrystalline material anymore. This has not come true. And therefore it is interesting to understand in detail also these multicrystalline cells. And so we have a bulk line, there are variations by more than an order of magnitude, and leading to inhomogeneities of the distribution, in particular of J01 and JSC. But also for monocrystalline cells, the depletion region recombination current characterized by this J02 and ohmic shunts and also breakdowns are always local phenomena, as we will see later on. And moreover, it's clear to everyone that the effective series resistance is position dependent, and technological founds that cracks lead to inhomogeneous series resistance. And for detecting all these inhomogeneities and evaluating their influence on the efficiency, solar cell imaging methods are indispensable. And by looking for the physical origin of inhomogeneous characteristics, we have unveiled in the last 20 years a number of new physical mechanisms. I hope to explain this in the following. So let us start here. If you look in the textbooks for these equivalent circuits, or the most popular is the so-called one-diode model of a solar cell, that the current density is this exponential part minus JSC. Well, here the series resistance influence is still missing, but this simple leads to the prediction of the open circuit voltage being this. And but a real solar cell does not behave like this. So if you look at the dark characteristic, so the dashed characteristic is the expected one according to this, and the drawn characteristic here is a measured one, a really measured one. And we see that well, this was modeled here by PC1D, which is also a homogeneous solar cell model, yes, to reflect the data of this solar cell, you know. And we see that the global J01 is somewhat higher than expected, but J02 is orders of magnitude higher expected and has a too large ideality. So the shallower the slope of this J02 branch, the higher is the ideality factor. And this also leads to some smaller differences in the illuminated characteristic. So in this theoretically we should expect a higher efficiency than in reality. And even if we simulate the illuminated characteristic from the dark one, so including the series resistance, we are not exactly the same, so we have some differences here. And another very strong difference is under reverse bias, so we expect that a solar cell with a doping density of 10 to the 16 breaks down only at 60 volts, minus 60 volts, but in reality we have something like this. So these are strong deviations from the expected. The question is, where do they come from? And ohmic shunting is not explained by any classical diode theory. So the solar cell imaging methods we are using and which are generally used are basically three. The oldest one is Elbic light beam induced current mapping. It's used since 1979. This was the oldest reference I have found on that. And probably you know it's a moving light spot. Or the cell is moved below a light spot, and it images basically the short circuit current density at a certain wavelength, because it's performed monochromatically. So you can image the external quantum efficiency and the internal quantum efficiency if you also measure the reflected light. And so if you have several wavelengths available, so the spectral information yields you can produce the JSC under AM 1.5. You can measure effective diffusion lengths and can distinguish between bulk and surface recombination and things like that. And the most prominent commercial system of this Elbic is, for example, the Loana system of PV Tools. It's a German company. Then lock-in tomography came next historically. It was known, actually we have not invented this, we were just the first to use it for solar cell inspection and also for other. It is known since 1988, and we have used it for solar cell investigation since 2000. And dark log image tomography, so abbreviated here, DLIT, is it basically images the local dark current density. I will come back to this later on, and there are many variants of this technique. And there are many commercial vendors, and one of it is Infratech with a PV lid system. So the results I'm showing here are basically from systems from them. And the youngest method is luminescence imaging, which is prominent also here, and it is also used since 2005 by Fuyuki for electroluminescence, and Thorsten Trubke has used it on solar cells for series resistance imaging first. And this technique basically images the local diode voltages and effective diffusion lengths by this also. And I will show then in my next talk that there are many new evaluations, new ways to evaluate these images. This will not be the content of this talk, and the most prominent commercial system is the system by BT imaging. Here I will concentrate on results on lock-in thermography. I will show results of the so-called local IV evaluation method. I cannot go into details now. Please wait for the talk after 2 weeks from now, where I will introduce this technique in more detail. The basic thing is the following. So we measure dark lock-in thermography images at 4 different voltages, 3 forward biases and 1 reverse bias, and then we fit all pixels to a 2-diode model. And this is a 2-diode model. This exponential part of the first diode describing bulk and surface recombination. And this is the so-called second diode describing a recombination in the depletion layer. And this is an ohmic term. So that's the formula for the dark characteristic, including the influence of the effective series resistance RS. So, and if we actually all pixels in the image are fitted to this 2-diode model. So the results are images of J01, J02, N2, which is also used as a local parameter, and the ohmic conductance, which is the inverse of the parallel resistance, you know. So we need a series resistance images, which is usually calculated from evaluating the local diode voltages, which we can obtain by luminescence imaging. I will explain this in detail in the next talks. So the JSC images, if we also want to simulate illuminated characteristics, we need an image of the short circuit current, can be simulated from J01 or loaded. Also, this will be explained in the next talk. So, and then this technique leads to a simulation of the local and global dark and illuminated IV characteristics. So, and this is results of this evaluation I will show later on. And then also local solar cell parameters, global or for selected regions, can be simulated. So I will show examples later on. So this very briefly to this so-called local IV method, which is an evaluation of dark lock-in thermography. Further methods we have been using was SEM-EBIC, which is physically very close to LBIC, to light beam induced current. The difference is that in EBIC you have not such a large penetration depth. So you investigate only the uppermost part, so you are not very sensitive to lifetime variations. So you need strong lifetime reductions to see anything. On the other hand, you have a much better spatial resolution because the electron beam can be focused much finer. So, and I have to remind you, if we have ohmic shunts, then we don't have the usual recombination contrast, which is sketched here. So if we have a grain boundary, for example, we see it dark because part of the generated excess carriers are recombining before they flow back. But if we have ohmic shunts, we have a current distribution contrast, which we have explained already in 2004, which means if our beam is here, so the current can choose to flow to the shunt or to flow to the current amplifier, which also represents a short circuit on its input, you know. And then depending on the position, so the detected current becomes lower if we come closer to the shunt. That has nothing to do with recombination. It's a current distribution contrast. So, and then we have used transmission electron microscopy and scanning transmission electron microscopy for identification as crystal defects, as you will see later on. So now let me come to the main part, which is the origin and quantitative influence of J01, J02 and parallel resistance inhomogeneities. So I hope that I can make clear that the physical origins of J01 and J02 inhomogeneities and of material-induced ohmic shunts will be reviewed. And on two examples, which is one industrial standard technology cell, so a so-called back surface field cell with a large area aluminum contact, and one industrial PERC cell on high performance material, which was given to me by Trina Solar. And on these two examples, I will describe the quantitative influence of such defects on the efficiency of these typical cells. This will be analyzed. So let me start with J01 inhomogeneities. So actually, J01 is, as I've shown already in this little formula at the beginning, it's the most important solar cell parameter because it determines the open circuit voltage. And the value of J01 depends on the bulk lifetime and on the back surface recombination velocity. And this bulk lifetime is strongly influenced in this multicrystalline material by crystal defects like dislocations and grain boundaries. And so luminescence and albic in combination with surface diffraction here, electron orientation measurement, have revealed that the grain boundaries with the strongest recombination are small angle grain boundaries. This was revealed already before we did it, so from Japanese colleagues, and so this is clear now. And so I will show now in the next slides our so-called STEM investigations that have shown that a special type of dislocations, so-called perfect Lomer dislocations, are responsible for or are dominating the recombination activity of these small angle grain boundaries. So what we have done. So at the left, we see this is lock-in tomography based diffusion current. So the diffusion current is the first diode current in this two-diode model, which is due to the bulk lifetime mostly. And the maximum, the defect regions, it shows a maximum. And these two maximum regions, here is the corresponding EBIC image of this region. Here we see these dark lines, and these dark lines are small angle grain boundaries. This is visible here, there's the orientation, and we see in all these regions we have basically the same basic orientation, and these red lines are small angle grain boundaries, which have an inclination of only a few degrees. And in these boundaries, we have prepared a number of samples, actually 6 samples, I think it was, from 2 grain boundaries, and we have performed so-called low-angle annular dark field, LAADF, scanning transmission electron microscope. So we have a scanning transmission microscope which produces an extremely fine beam of only angstroms in diameter, smaller than the diameter of an atom. And we detect the outcoming electrons which are scattered by a small angle. That's actually this. And in this imaging mode, the single atom rows, of course it must be oriented, they show up as dark spots. So these are really single atom rows, what you see, going into the dark. And here, for example, here you see that is stacking faults. So if these atom rows, if they make a kink, then this is a stacking fault. And if you have regions of internal stress, they show up as bright regions, like here around and there. So, and I have to explain, so usually grown-in dislocations, in most of the grown-in dislocations in solar cells are split into partials. This is they do in the process of cooling because of minimizing their energy. And then they have these stacking faults in between, But some of these dislocations, they are unsplit. And if they have a certain Burgers vector and a certain orientation, then there are so-called Lomer dislocations. So in the paper, we have described exactly what this is. So these are Lomer dislocations, and these are other. And the ratio from Lomer dislocations to the other dislocations depends on the orientation of the grain boundary. And these were bent grain boundaries. So they did not have the same epic contrast and recombination contrast in each position. And we have, as I told, we have prepared in 6 positions. And then we have made some statistics. So we knew from the epic results, we knew the contrast in percent. And then we have measured, by evaluating the TEM results, the density of dislocations, of the total dislocation density, irrespective of their type, and the density of only Lomer dislocations. So the red points are if we count only the Lomer dislocations, and these points are if we count the total dislocation density. And you see the total dislocation density does not correlate with the contrast, but the Lomer dislocation density does. So we believe that the recombination activity of these grain boundaries clearly correlates with the density of Lomer dislocations, but not with the total dislocation density. And therefore we think that we have identified the major recombination cause. I mean, this does not answer the question how to avoid this. This would be the next thing. Okay, now what do these low lifetime regions, which we know now where they come from, what do they make for the solar cell? Under one sun, we have, this is a standard technology cell, and we have a global J01 of 1.7 picoamps, and in the best region we have 1.0 picoamps. And this is the measured and also the simulated open circuit voltage, and this is the efficiency. And in the best regions outside of these dislocated regions, we expect a much higher open circuit voltage, plus 15 millivolts, and here plus leading to an efficiency of plus 0.8% absolute. And for the PERC cell, it is even stronger. On the one hand, the currents are lower, the dark currents are lower. So the J01, the global J01 is only in the 280 femtoampere per square centimeter region, and in the best region it is as low as 154 femtoampere. So here the expected, if we could get rid of the defects, we would win 21 millivolts and 1.1% absolute in efficiency, which leads us to the conclusion that the grown-in defects in multicrystalline silicon, they significantly increase J01 of the cells, which could be expected now, but now we can quantify this. Yeah? So the dominant recombination activity is obviously due to these perfect Lomer dislocations, and these crystal defects degrade the efficiency in a typical multicrystalline cell by 0.8% and by PERC by 1.1%. In spite of the fact that the PERC cell was on high performance material. So, and this defect-induced degradation is mainly due to an increased J01 and occurs mainly by reducing VOC and JSC. So this is only weakly dependent on the illumination intensity. Now let us come to J02. And so these are, by the way, results which date back from my working stay here some years ago. There I have started with these investigations. So we have found, and it was already known before, if we have monocrystalline cells with planar technology, where the cell edge is passivated by an oxide, these cells behave as expected, as we have seen at the beginning. So with an ideality factor of unity over a large voltage range. But if we scratch them, then we convert them into the characteristics as we measure it in usual industrial solar cells. So obviously, diamond scratches generate the types of defects which are responsible for the real characteristics. And this was found already in 1994 after my stay here, and was later on reported here in 2009. So, and why we have these high ideality factors? So it is because the recombination is beyond Shockley-Ritt-Hall recombination. Shockley-Ritt-Hall recombination means that we have one level and 2 steps. So first the electron is captured, then the hole is captured. But at extended effects, we have such a high concentration, local concentration of defects, that their orbitals overlap, which allows interaction between the levels. So we can have multi-level recombination as sketched here. And the simplest model for multi-level recombination is deep donor acceptor pair recombination. And this can easily be modeled. And that's what we have done. So if we have extended effects, which may be surface states at the edges or interface states to precipitase or scratches, as I've shown, crossing the pn-junction, then we can expect multi-level recombination. And first simulations have shown this already 2006. And now Silke Steingrube, who was a PhD student of Pietro Altamat, has realistically simulated this and managed to fit measured characteristics with this model. So we think that we understand this now, and let us show the influence. So here we see a typical J01 current here, and we see that it is concentrated at the edge. So maybe we should not consider these inner, that's a quite old cell, so these are scratches more or less, and these are cracks. But here we have this edge current, and now I have evaluated with a local IV method the whole cell and only the inner part of the cell without the edges. And I found out that at 1 sun illumination intensity, the influence of the edge is very weak, so the fill factor would only improve without the edges by 0.5%. And the efficiency by 0.1%. However, at 0.1 sun at reduced intensity, the fill factor will be increased, if we wouldn't have the edges, by 0.4% and the efficiency by 0.3%. And very similar numbers. So here at the right, I just for memory, I show you the J01 image, and you see the J01 image is very different to the J02 images. And this proves that this method really can distinguish between these 2 types of currents, you know. So, and here in the PERC cell, we have the same, that only in the J02 images we have this strong edge current, which is not visible in the J01 image, and the numbers are nearly the same. So which brings me to the conclusion that J02 currents are always local phenomena, because they are connected with these extended effects, but macroscopically they are small. And so the homogeneous J0 current, which according to the textbooks is also existing, but it's negligibly small in all these solar cells. It's so small that it cannot be detected by lock-in thermography. So this J02 current flows where extended defects with a high local density of gap states are crossing the pn-junction, and this high density may lead to ideality factors larger than 2 due to multi-level recombination. So I already have shown the numbers. So this J02 current degrades mostly the fill factor and mostly by small illumination intensities. Now let me come to ohmic shunts. So in multicrystalline material, so the most prominent ohmic shunts are due to silicon carbide filaments crossing the whole cells. This was also identified by us already here in 2004. And we have seen, so we have dissolved them and have measured them separately and have found that they are N-conducting. It is N-conducting silicon carbide, and these are filaments which are growing preferably in grain boundaries. So they are arranged in lines, you know. And this is how it looks in lock-in thermography. So if we have the same image at plus minus 0.5 volts, then it is an ohmic shunt. And if we have prepared here, we have from the back side, we have dissolved some material in HNO3 and did not wipe. And then they come out, and these are these silicon carbide filaments. And if we make EBIC at the back side, we see that if beam comes close to these things, so we have a collection efficiency close to 1. So it is because these they are n-conducting, yes, you know, and this is the model actually, and they are directly connected to the n plus emitter. So actually they extend the p-n junction across the whole area. And of course, if they then come to the back contact, they short circuit everything. That's the mechanism of this. This was identified here in 2007. So this is another solar cell, because the cells before, they didn't show prominent ohmic shunts. This was a shunted cell, multicrystalline cell, having this type of defects. And we have evaluated it using the so-called virtual cut shunt function, which allows us to replace the properties of a certain selected area by the properties of the surrounding. So we can virtually cut out the shunt and leaving the cell intact, well, within this software. And this is a delete image at plus 600 millivolt. That's high enough to show also the J01 and J02 current. And at minus 1 volt, it looks like this. And so all defects which are appearing in both images are the ohmic shunts. And so one by one, I have cut out them. And then at one sun, the reduction of the fill factor is 3.3%. Absolutely, it's quite something. VOC only 2 millivolts. And the efficiency, at least, it influences in this heavily shunted cell by 0.8%. But at 1.1 sun, the reduction of the fill factor is 25.3%, so really amazing. VOC by 22 millivolt and the efficiency by 5.1%. So I will come to the conclusions later on, but this is much stronger than the. But let me remind you, this is a heavily shunted cell. So, but there are other ohmic conductivities, and the most interesting one is also ohmic conductivity at extended defects. So this also was made by these scratching experiments. So the virgin solar cell did not have any measurable ohmic conductivity under low reverse bias. This is a reverse bias. But depending on the load, so the stronger the load is, and the closer we come to the p-n junction, and if we cross the p-n junction with the diamond, then we get some ohmic conductivity, also under reverse bias. And so this is hopping conductivity, and this was proven by measuring the temperature dependence of this reverse bias here, and that's our model. So we believe that we generate a number of defects across the whole energy gap, you know, and then they are so close that they interact with each other, they overlap and lead to this hopping conduction. And this is proven here by this logarithm of the reverse current over 1 to T11 to the power of 1/4. That's a very special temperature dependence, and it is predicted by Mott's theory and for other systems. But this special temperature dependence is only expected for this kind of hopping conduction. And we see here that's a monocrystalline cell. Don't consider the signal in, there's a log-in tomography at -1 volt, and we see we have a very weak but measurable ohmic current here in these edge regions, where we also have seen the J02 current. Okay, other sources of ohmic shunts are due to potential induced degradation. And they cause ohmic shunts and J02 currents, and we also have contributed to these identifications together with a group of Volker Naumann and co-workers at Fraunhofer CSP in Halle. And so we have seen these degraded cells, the positions of strong PID. So the looks very cloudy in log-in tomography, because log-in tomography doesn't have a good spatial resolution. But if we look with EBIC, then we have this current distribution contrast, which I have explained at the beginning, and we see these dark spots. And in some in these positions, then some TEM specimen have been prepared, and on this very high resolution electron dispersive X-ray, measurements have been performed, and this is the sodium signal. It turns out that these defects are planar defects lying on 1-1-1 planes like stacking fouls, but they are not simple stacking fouls. They are planar defects heavily coated with sodium, and this is proven here. And this is actually the physical model proposed by me, that the ohmic conductance is, as I have shown in the last slide here, due to the Sopping conduction, and the J02 is, as I have explained it before, for the J02 currents like this. So here we have both. At the beginning, when the local density is still low, we have dominant J02 current, and then with a stronger degradation, so the ohmic shunting. So this brings me to the conclusion to ohmic shunts. So like the J02 currents, also ohmic shunts are always local phenomena. There is no homogeneous ohmic shunting. Ohmic shunts reduce mainly the fill factor. Stronger shunts also reduce VOC. So the efficiency degradation due to ohmic shunts is strongly illumination intensity dependent, as I've shown at the beginning. Their influence drastically increases with reducing illumination intensity. And this property is stronger than in the case of J02 is due to the fact that the ohmic shunt current drops much less with reduced bias than the diode current. The diode current, dominant diode current, is still dominated by J01. And the dominant material-induced ohmic shunts in multicrystalline cells are due to these silicon carbide filaments. Other ohmic shunts are due to aluminum particles, cracks, edge surface states, and also PID defects. Okay, now let me come to the last point, breakdown sites. So in the textbooks we found two breakdown mechanisms, which are avalanche breakdown and internal field emission, which is also called Zener breakdown or tunneling. IFE is an abbreviation here. And avalanche means that in the field, electric field of the pn-junction, an electron is accelerated and then it scatters, and then it releases its energy by producing another electron-hole pair. That's a so-called avalanche effect, which is also exploited in the avalanche photodiodes. And the Zener effect is the following. It dominates for high doping densities. Then here this gap becomes very small because of the high electric field. And then the electrons may tunnel through. And this is tunneling. These are the two. And this dominates for high doping. With our solar cells, we are in the moderate doping region. So for us, avalanche breakdown at minus 60 volt is predicted. The question is why we have already at lower voltages breakdown. So we have started in now around 2010 or so. We have started with these investigations. And we have found that globally, that's a global dark characteristic, reverse characteristic, and if this is for 25 and 80 degrees centigrade, and we have seen in the low bias or low reverse bias region, we have a positive temperature coefficient of the current, but in the high bias region, we have a negative temperature coefficient. And the only mechanism which leads to a negative temperature coefficient is avalanche. So, but the voltage is much lower than we expected. And we see also the images are different. Here at minus 8 volt, we have some number of breakdown sites. So then at minus 12 volt, we have this, what we have called type 2. So this is below this limit. And above this limit, above minus 13 volt, here at minus 15 volt, so some breakdown appear which have not been there. Well, and so all these breakdowns mechanisms have been identified. So this early breakdown, or we called it type 1, was identified by Dominic Lausch and co-workers. And it is due to aluminum at the surface. And here I show the mechanism. So if we have a particle of aluminum at the surface, and then we have the final contact firing step, then it alloys in and leaves behind a P+ region, because it overcompensates the emitter there. The emitter is N+. And then here we have N plus P+, and that's a tunnel junction, and or a xenodiode actually, and it leads then to breakdown and also to visible light, as it is known for these Zener breakdowns. So that's a mechanism. And then type 2, it's very different. It is due to iron silicide needles, which we have found in grain boundaries crossing the pn-junction. Yes, and these needles are in the grain boundaries crossing the pn-junction. Yes, and here we show that the EL plus rebel, this means reverse bias electroluminescence. So in reverse bias, if we have some local breakdown size, they show up as bright spots. And here they are superimposed to the dark lines coming from electroluminescence, from standard electroluminescence. And you see the breakdown sites are only in the position of these dark lines. So this has something to do with each other. And Schneemann and co-workers at the Forschungszentrum Jülich, they have found that by locally detecting these luminescence, that different breakdown sites have different breakdown voltages, and also their slope can be different. And we have performed in these positions TEM transmission, electron microscope, and EDX, and have seen that in the position of these breakdown sites we have iron silicide. Actually, it is iron disilicide, and it's quasi-metallic. So, and if it is, that's our model. So in the N+ emitter, we expected to have an ohmic contact, and in the PN junction, it's a kind of Schottky contact. And in addition, we have this needle function, so the field enhancement at the tip. So the mechanism is Schottky breakdown, which is thermionic field emission, which is shown here. It goes like this. Influenced by the tip effect, and depending on the geometry, the breakdown voltage may vary from site to site. And all breakdown sites are phase resistance limited. Okay, now let's come to the third type, which is avalanche breakdown. So, and we have found in multicrystalline material, which is acetic etched, that in these positions of this breakdown, we find this funnel-shaped edge pits. This is a cross-section through an edge pit together with a dislocation. It's a special type of dislocations. You have to know that actually this etching procedure is optimized not to lead to preferred defect etching. Nevertheless, some special types of defects lead to edge pits. And in these edge pits, we have it looks like this, and then here this is 200 nanometer, and the depth of the PN junction is 300 nanometer, a little more. So we expect here to have the edge of the PN junction spherically bent. And there's old literature that have calculated that a spherically bent PN junction with 300 nanometer diameter just leads to a reduction of the breakdown voltage from -60 to -13 volts. And this really explains this. And we also have done these investigations on alkaline etched material, which doesn't show any edge pits. And here we have found that we have preferred phosphorus diffusion at grain boundaries. So this is a grain boundary going vertically. And here we have in two positions, we have done FIP cuts and have made EBIC electron beam induced current on these FIP cuts. And already outside of the breakdown site, we have seen a little dip here, which means we have preferred phosphorus diffusion in this grain boundary. But in the breakdown site, it is much stronger. So these breakdowns are obviously due to some line type defects in grain boundaries where we have preferred phosphorus diffusion, and then we have the same mechanism. So the nature of these defect-induced, in particular the proof between avalanche and non-avalanche can be done by special lock-in thermography methods which allow to image the multiplication factor. And here we see there where we have only this high voltage breakdown, we have a multiplication factor much larger than 1. 1 would be no. And also the temperature coefficients are different and also the slopes are different. So this all can be measured. And finally, so if we have a monocrystalline cell, then from these breakdown mechanisms, actually only the aluminium-induced breakdown is expected to occur. But we also found in also perfectly made solar cells, we found some breakdown. And it is in particular at the edges. So this is, by the way, the same monocrystalline cell. I have shown some results already before. This is the J02 current. And this is the breakdown current at minus 15 volts. And we see here where we have the local maxima of the J02 current, we also have the local maxima of the breakdown. So we believe the mechanism is basically the same as the ohmic current, which we also have found by this extended defects there, with the exception that it is now field dependent. So we already in the IV characteristics I have shown before there's some positive slope or some super there was some super linear behavior which pointed to field dependence, and I believe that this current, it is trap-assisted tunneling in the edge region, but multi-trap resisted tunneling. And here, this is a nice image of lock-in thermography, which was produced by Eric Gerritsen of CEA Ines in France. And it shows a daylit image of the monocrystalline module string at minus 300 volt, which is also about 15 volts per cell. And you see the breakdown occurs only in the edge region. This is very different to multicrystalline material. So the conclusion to pre-breakdown sites are the following. Theoretically, silicon solar cells should break down at minus 60 volt. In reality, it makes much earlier. And so the dominant pre-breakdown mechanisms are early breakdown, close to ohmic, aluminum particles at the emitter, defect-induced breakdown, iron silicide needles in the grain boundaries, early avalanche breakdown, at pitch or edge pits or preferred phosphorus diffusion defects. And last but not least, trap-assisted tunneling in edge regions where extended defects, for example, surface stage, are crossing the pn-junction, and I propose to call this type 4 mechanism. And this should be dominant for monocrystalline cells. This brings me to my final conclusions. So the local IV dark lock-in thermography evaluation method, which was used in the first part of the talk, enables a quantitative local efficiency analysis, though its spatial resolution is limited. And this is the only method that may reliably separate J01, J02 and ohmic current distribution from each other and may quantify also breakdown currents. By simulating dark and illuminated characteristic of these whole cell and of selected regions, this method allows to check the influence of certain defects on cell parameters. And in particular, the virtual quotient function allows to exclude local defect regions and evaluate their influence. And this software is available and is very useful for understanding local reason for poor cell efficiency. And understanding the dark current of solar cell is a key for maximizing their efficiency, in particular open circuit voltages in the fill factor. And by detecting inhomogeneities of the cell current by dark lock-in tomography and physically investigating the root causes of local currents, in the last 15 years we have identified the nature of many previously unknown conduction mechanisms. Namely, we have identified the dominant recombination mechanism for grown-in defects in multicrystalline cells, the nature of J02 currents, the nature of ohmic currents, and of most of the breakdown mechanisms except of this type 1. Now we understand much better than before the limitations of silicon solar cells, in particular for VOC and the fill factor of multicrystalline cells. And I thank for some supports, and I have to thank many people for cooperation, in particular my last co-workers Jan Bauer and Felix Frühauf, and Infotech for providing the system. Thank you for your attention.